But we know many smooth things are smooth only because we're too far away to see the grain. A digital photo looks smooth until you zoom in. Then you see pixels. A movie looks continuous until you notice its frames. A smooth wall looks smooth until you're close enough to see texture. The Planck scale is the zoom-in point, where the smooth space-time description is expected to stop working as a complete story. This does not mean space-time is literally made of tiny cubes like Minecraft. That's a cartoon. But it does mean the equations of relativity treated as a smooth geometry likely aren't enough at extreme scales. We may need a quantum description of geometry itself. And that's the heart of the search for quantum gravity. Different approaches try different answers to the same question. What is space-time made of, if not a smooth, continuous fabric? Some approaches suggest space-time has a discrete structure, like a network, a graph, or a causal set of events connected by cause and effect relations. In those pictures, distance and geometry arise from the structure of the network. A simple analogy: a city map. The distance between two places is not about continuous space. It's about the network of roads. If you're traveling by roads, connectivity is what matters. Geometry emerges from the network rules. Other approaches, like loop quantum gravity, aim to quantize geometry itself, making areas and volumes come in tiny chunks rather than being infinitely divisible. A life analogy: money. In many systems, you can't have any arbitrary amount. You have cents. There's a smallest step size. Your bank balance changes in discrete increments. That doesn't make money less real. It just means the system has a smallest unit. Some approaches in string theory suggest that the fundamental ingredients aren't point particles at all, and that space-time dimensions and geometry can arise from deeper quantum consistency conditions. And string theory is also one of the places where holographic dualities were developed most sharply. Now, here's the honest boundary line. We have very strong evidence for quantum mechanics. We have very strong evidence for general relativity. We do not yet have direct experimental evidence that cleanly selects a single theory of quantum gravity. So when people say space-time is definitely emergent, they're going beyond what's fully proven. But when they say there are strong reasons to suspect the smooth space-time picture is not fundamental, that's a fair summary of where the theoretical pressure points are. Now, the transcript also flirts with the idea that the universe might be rendering reality as needed, like a video game. That's where we need to be extra careful. The scientific version of rendering is not someone is running a simulation. The scientific version is something like, the classical world may be a coarse-grained output of deeper quantum information processing, and what looks like continuous space-time might be an effective description that emerges when you average over huge numbers of degrees of freedom. That's less spooky, more precise, and it doesn't require a cosmic gamer. Here's a practical analogy. When you use Google Maps, you don't see every atom of every road. You see a simplified model: streets, routes, traffic colors. It's real enough to navigate, but it's not the raw territory. It's a representation optimized for decisions. Physics may be telling us something similar. Space-time might be the representation layer that becomes useful at large scales, when you're dealing with planets, stars, and galaxies, while the underlying layer is more naturally described in terms of quantum states, information, and their relationships. And this is where cosmology quietly walks onto the stage. Because in cosmology, the space-time picture is incredibly powerful. It describes an expanding universe. It describes black holes. It describes gravitational waves. It describes the evolution of galaxies. So, even if space-time is emergent at the deepest level, it's still astonishingly real at the level where we live. Emergent doesn't mean optional. It means layered. Which brings us to the next natural question. One the transcript raises in a dramatic way. If space-time might not be fundamental, what about time? Is time a basic ingredient? Or is it something that shows up when systems get complex, when entropy increases, when memory becomes possible? That's the next layer. Time, causality, the arrow of time, and why the flow of time might be as much about thermodynamics and information as it is about a universal ticking clock. And we'll keep it grounded. No heavy math, just the clean ideas and the best analogies. Let's talk about the thing you can't not experience. Time. You can ignore distant galaxies. You can ignore quantum fields. You can even ignore dark matter and still have a normal day. But you can't ignore time. It's the one feature of reality that feels the most absolute, the most personal, the most undeniable. It's always there, pushing moments from future to present to past, like a conveyor belt you never asked to stand on. So, when people hear that physics might treat time differently, or even treat time as non-fundamental, it hits harder than atoms are mostly empty space, because empty space doesn't ruin your schedule. Time does. Here's the first important move. Separate two questions that people often mash together. 1. What is time in physics? 2. Why does time feel like it flows? Physics can address both, but they aren't the same problem. In everyday life, time is a clock reading plus the feeling of passing. In physics, time is more like a coordinate, a way of ordering events and measuring change. And in relativity, time is tightly linked with space. General relativity tells us that time is not a universal metronome ticking the same for everyone. It depends on motion and gravity. Clocks at different speeds or different gravitational potentials tick at different rates. That's not philosophy. It's engineering reality. GPS has to correct for it. So already, long before quantum gravity, physics has this uncomfortable message. Time is real, but not absolute. Now comes the next twist, and this one is more subtle. Some deep physics equations don't put time in the starring role the way we expect. When physicists try to combine quantum mechanics with gravity, when they write down candidate equations for the whole universe, time can start looking less like a basic ingredient and more like something that emerges from relationships between things. If that sounds abstract, here's a life analogy that makes it concrete. Imagine you have a playlist but no timestamps. You can still talk about before and after based on song order. You can still talk about change. But the feeling of a clock ticking is not built into the playlist itself. It comes from an external reference, like a timer, or from the rules of playback. Similarly, some approaches to fundamental physics suggest that at the deepest level, you can describe the universe as a network of relationships or states. And what we call time may be a way of organizing those relationships, especially when you zoom out to large scales where clocks make sense. This leads to one of the most famous, mind-bending but not mystical ideas, the block universe. In the block universe view, The universe is a four-dimensional space-time structure. Past, present, and future are all part of the structure. The flow of time is not something the universe does. It's something conscious beings experience as they move along their world lines and create memories. That can sound like the future already exists, which feels unsettling. But you can treat it as a geometric statement rather than a fatalistic one. It doesn't mean your choices aren't choices. It means physics doesn't necessarily give one moment a special now tag. A listening friendly analogy. A whole movie file exists on your laptop. The movie contains the beginning, middle, and end at the same time, as data. But you experience it frame by frame when you press play. The present moment of the movie is whatever frame the player is currently showing. The file doesn't have a glowing sticker that says, "This frame is the real present." The player creates the experience of now. The block universe idea is like saying space-time is the movie file. Your consciousness is the player. Now, that analogy is not a proof of the block universe. It's a way to make the concept feel understandable. The reason physicists take block universe-style thinking seriously is because relativity treats time as a coordinate and doesn't privilege one observer's now as universal. Two observers moving relative to each other can disagree on what events are simultaneous. That makes a single universal present hard to define objectively. So, if you try to build an objective now, relativity keeps tripping you. Okay, so physics has reasons to treat time differently than your intuition does. But we still haven't answered the second question. Why does time feel one way? Because even if the universe doesn't have a universal present, you still have a very clear psychological arrow. You remember the past, not the future. Eggs scramble. They don't unscramble. Smoke spreads. It doesn't gather back into the cigarette. A messy room becomes messier, not magically cleaner. That one-way behavior is called the arrow of time. And the best explanation we have for the arrow of time isn't time has a built-in direction. It's thermodynamics. More specifically, entropy. Entropy is often described as disorder, but that's a bit sloppy. A better listening-friendly description is entropy measures how many microscopic arrangements correspond to the same macroscopic situation. A tidy stack of cards is one arrangement. A shuffled deck can be arranged in astronomically many ways. If you shuffle, it's easy to go from tidy to messy because there are so many messy states to fall into. Going from messy to tidy by random chance is possible, but ridiculously unlikely. So the direction we experience toward greater entropy is not because laws of motion demand it. It's because the universe started in a very low entropy state, and there are vastly more high entropy states available. A life analogy. Imagine you drop a jar of beads. There are many ways for beads to scatter across the floor, and only a tiny set of ways for them to arrange themselves back into the jar. The laws of physics allow either arrangement, but probability heavily favors scattering. That probabilistic bias becomes a direction in practice. And here's the key connection to your experience. Memory creation requires entropy increase. To store a memory, whether in your brain, a notebook, or a hard drive, you have to physically change something. That change involves energy flow and typically increases entropy overall. The act of recording information is tied to thermodynamics. So the reason you remember the past and not the future is not because the universe insists on pastness. It's because information about the past gets recorded in physical traces as entropy increases. The future doesn't yet have traces because those traces haven't been formed. In a sense, we experience time flowing because we are systems that continually generate records. You are a record-making machine. Congratulations. Also, sorry. Now, the transcript you uploaded leans into a dramatic vibe. If time is emergent and observation matters, maybe causality is slippery. Maybe the past is not fixed. Here's the more careful scientific stance. Quantum experiments can make classical storytelling about what happened less straightforward, especially when you condition on specific measurement outcomes. But that doesn't mean you can rewrite history like editing a document. It means the classical notion of a single definite story for unmeasured properties isn't always applicable. The past, as we record it, macroscopic events with robust traces, is extremely stable. The weirdness lives mostly in the microscopic description and in how you assign reality to unmeasured alternatives. So we can say something interesting without pretending the universe is trolling us. At the deepest level, time might be a way of organizing change and correlations. At the everyday level, time feels one way because entropy and memory create a strong arrow. And between those levels, the now you feel is likely a product of how brains integrate information and build experience. This bridges nicely back to the interface theme. If space-time is an emergent description and time's arrow is tied to entropy and information, then your lived experience of time, smooth flow, solid present, fixed past, can be seen as the brain's stable interface to a deeper reality that doesn't naturally come with a glowing present moment label. Again, not fake, just layered. And now we're ready for the synthesis, the place the transcript was aiming for the whole time. If perception is a model, matter is fields and rules, quantum mechanics is about information and correlations, space-time might be emergent, and time's arrow is tied to entropy and records. Then it's natural to wonder whether the deepest stuff is not matter at all, but something like information. Not information as in gossip. Information as in the number of possible states, the constraints on states, and the rules that update states. That brings us to the final section. The it from bit style idea. What's mainstream versus speculative, and a conclusion that's spooky only if you want it to be, but scientifically meaningful even if you don't. At this point, we've pulled on a lot of threads, so let's do what good science writing should always do near the end. Gather them into one clear picture, and then draw a careful boundary around what we know versus what we're guessing, because the original transcript has a dramatic title. The universe may be a deception, but the most useful version of its message is calmer than that. Reality might be layered. The layer you live in is real, stable, and usable. But the deepest layer might not look anything like objects in space over time. That's not a horror twist. It's what happens when you keep zooming in and zooming out with modern physics. So here's the synthesis, step by step, without hype. First layer, your brain builds a usable world. You don't experience wavelengths, pressure gradients, or electrical potentials directly. You experience color, sound, and touch. Your brain compresses an overwhelming stream of data into a stable scene of objects and events. That's not a conspiracy. It's survival engineering. If you saw the raw data, you'd be overwhelmed. So the brain gives you icons: chair, face, danger, food. Second layer. Matter is not little hard pellets. Modern physics describes what we call matter as patterns in quantum fields. The solidity of a table is mostly electromagnetic and quantum rules resisting overlap, not tiny bricks making contact. So the everyday object world is still real, but it's an emergent description of deeper behavior, like traffic is an emergent description of many cars. Third layer. Quantum mechanics forces us to rethink what definite means. Experiments like the double slit show that interference appears when paths are indistinguishable and disappears when which path information becomes available. Bell tests show nature produces correlations that can't be explained by local pre-written instruction sheets. This doesn't mean anything goes. It means some classical assumptions can't all be true at once. And now we reach the step that makes the transcript's title feel tempting. If objects are emergent patterns, and quantum reality is fundamentally about probabilities and correlations, why are space and time treated as unquestionable? That's where the pressure from black holes, holographic thinking, and entanglement-based ideas comes in. They hint that space-time itself might be an effective description. Very powerful at large scales, but not necessarily fundamental. Then time adds the final twist. Relativity already tells us time is not universal. Thermodynamics tells us the arrow of time is tied to entropy and record-making. Some deeper theoretical approaches suggest time may not be a primitive ingredient in the deepest equations, but something that emerges when you coarse-grain and track change. So, what's left as a candidate for the bottom layer? This is where the information idea enters. When physicists say information in this context, they don't mean Wikipedia. They mean something like how many states are possible, what constraints limit those states, how states can transform into other states, what correlations exist between parts of the system. In other words, structure, rules, and relationships. Now, why is information such a popular endpoint? Because it keeps showing up in the deep places. Black holes behave like information storage objects with strange bookkeeping. Quantum mechanics is basically a theory of probabilities, amplitudes, and correlations. Information like objects. Thermodynamics links entropy to information and to the arrow of time. And quantum gravity research repeatedly bumps into the idea that geometry might be derived from deeper relational data. So, the transcript's computational universe, Ars IT from bit vibe, is a way of saying, maybe physics is fundamentally about information processing, and what we call matter, space, time are higher-level representations of that processing. Now, here is the critical honesty line. There are 3 levels of confidence in this whole story. Level 1, very solid science. High confidence. The brain constructs a perception. Illusions show that clearly. Quantum field theory describes particles as field excitations and works extremely well in experiments. Quantum experiments demonstrate interference behavior and Bell inequality violations. Relativity shows time depends on motion and gravity. Thermodynamics connects entropy with a time arrow in everyday systems. These are not maybe. These are foundations. Level 2. Strong theoretical clues. Medium confidence. Black hole thermodynamics strongly suggests deep links between gravity, entropy, and information. Holographic dualities show that in some situations, a gravitational theory can be equivalent to a non-gravitational theory living on a boundary. Decoherence explains why the classical world emerges so robustly from quantum rules. These are not just vibes, but they're also not complete final answers about what the universe is. Level 3. Big interpretations. Speculative, but interesting. Space-time is fundamentally emergent from entanglement in our specific universe, possible but not proven. The universe is literally computation in a way that maps onto computer science cleanly. Metaphorically useful, literal claim is still speculative. Consciousness is required to collapse the wave function, a proposed interpretation not supported as a necessity by mainstream physics. The universe is deceptive in an intentional or simulation-like sense, philosophical territory not required by the evidence. This is where dramatic scripts like to camp out. It's fun, but you should know when you've crossed from experiment into interpretation. So, does the universe deceive us? A better scientific phrasing is, the universe doesn't deceive you. Your brain summarizes it. And physics agrees that the summary layer, objects in space moving through time, is not the deepest description we have. The scary feeling comes from a mismatch. Your intuition expects the deepest layer to look like the surface layer. Physics suggests the deepest layer looks like rules, fields, probabilities, correlations, and information constraints. That's not terrifying. It's just unfamiliar. Here's a final analogy that ties it all together without getting sleepy. Imagine you're playing a video game. On screen, you see objects, walls, characters, coins, gravity, time passing. Underneath, the game is not literally made of walls and coins. It's made of code, state variables, update rules, and memory. The game world is still real inside the game. It has consistent rules. You can't walk through walls. You can lose your coins. It matters. But if you looked at the underlying layer, you wouldn't see coin stuff. You'd see bits and rules. Now, I'm not saying the universe is a video game. That's an interpretation leap. But as an analogy, it works. It shows how a higher-level reality can be real and meaningful while being built from a deeper, very different kind of substrate. So, the most grounded conclusion is, reality is real, but it's layered. What you experience is a stable interface made by your brain. What physics describes underneath is not objects, but fields, interactions, probabilities, and information-like structure. And the frontier question, still open, is whether space-time and time themselves are emergent from that deeper structure. You've had this feeling before. Not the dramatic kind, the quiet kind. You're looking at your hand. It feels solid. It looks obvious. And yet, if you zoom in far enough, it's mostly empty space and rules. Now take that feeling and aim it at everything. Because this story is about a possibility that's both unsettling and strangely practical. What if the world you experience, objects, space, time, even common sense, is less like the raw universe and more like a user interface, a useful display, a dashboard? Not a lie exactly. More like a shortcut. Your brain doesn't build reality to be accurate in the way a physics textbook is accurate. It builds reality to keep you alive. It highlights what matters. It hides what doesn't. It turns a screaming hurricane of data into a calm, manageable scene. Chairs, faces, walls, sky. That's the first layer of the mystery. Then, physics adds its own plot twist. What you call stuff isn't really tiny hard beads. Modern physics describes matter as patterns and fields. The vacuum isn't truly empty. And at the deepest scales we can even talk about, space and time start acting less like a stage and more like something that might be built from deeper ingredients. And quantum mechanics, well, quantum mechanics is the part that refuses to behave politely. It doesn't just say your senses are limited. It says the universe itself doesn't always fit the classical story of things have definite properties, and measurement simply reveals them. Experiments force us to accept that correlations can be non-local, and that what becomes definite depends on how you ask the question. So, what are we going to do with all that? We're going to walk through the layers one by one, without getting lost in equations. We'll start with the brain. Why perception is more like a model than a mirror. Then we'll shift to matter. Why solid is a very persuasive illusion made of electromagnetic rules. Then we'll tackle quantum weirdness carefully. What experiments actually show and what they don't. Then we'll go after the big one, space-time itself, whether it's fundamental or whether it could be something that emerges from information and relationships. And finally, we'll return to the scary-sounding question: is the universe a deception? And translate it into a calmer, more scientific version. Reality might not be what it looks like, because what it looks like was never meant to show you the whole truth. That's not a horror story. It's a clue. Hello, and welcome to Sleepy Space Traveler. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. All right, let's start at the only place we can start, inside your head, where reality is assembled every second without asking for your permission. You don't see the world directly. That sounds like an insult. It's not. It's just how nervous systems work. You see a construction, a best guess, a model your brain builds in real time, using messy data and tight deadlines, because evolution does not reward philosophical purity. It rewards don't walk into traffic. So, before we even touch quantum physics or cosmology, we need one grounding idea. Your experience of reality is already an interpretation layer, not a lie, not a hallucination, a working interface. Think about the way your phone shows you a battery icon. That little bar is not the battery. It's a simplified symbol that helps you make decisions. You don't want to see raw voltage curves and internal chemistry. You want to know, am I about to die at 2%? Your brain does something similar with the world. It turns vibrations in air into voices. It turns scattered photons into a face. It turns chemical signals into danger. It turns millions of sensory fragments into a single smooth scene. And it does this so fast and so constantly that you don't notice the assembly process. You only see the finished product. Now, here's the first mystery piece. Even the things that feel most solid and obvious, color, sound, taste, are not properties sitting out there in the world in the way we intuitively think. Color is a classic example. Outside your head, there are electromagnetic waves with different wavelengths. That's it. No red, no blue, no sunset orange. Those are experiences your brain generates when certain wavelengths hit your eyes, and your visual system processes them. A simple life analogy. A song file isn't music until a player turns it into sound. The file is information. The player makes the experience. Light wavelengths are like that. Your brain is the player. This doesn't mean the world isn't real. It means your experience is not a one-to-one copy of the world. It's a translation. And translation always loses some detail and adds some structure. You can see this in how perception fails in predictable ways. Optical illusions aren't just party tricks. They're little windows into your brain's assumptions. Your visual system is constantly guessing about depth, lighting, motion, and object boundaries. Most of the time, it guesses correctly. Sometimes it guesses wrong, and the mistake becomes visible. That's useful, because it tells you something important. Perception is not passive. It's active. Your brain is not just receiving reality. It's inferring it. So, what is it inferring from? Mostly from incomplete data. Your eyes don't scan the world like a camera. Your vision has a high-resolution patch in the center and lower resolution in the periphery. Your brain stitches the scene together and fills in gaps. You move your eyes in little jumps, and your brain edits out the jumps so the world looks stable. Even the present moment is not a single instant. Your brain integrates information over short time windows. It smooths, it predicts, it corrects. A helpful analogy: watching a sports game on a slightly delayed stream. The video player buffers a little so it can present smooth motion. Your brain does its own buffering and smoothing. It trades perfect immediacy for coherent experience. That's not a flaw. That's a feature. Because the real world is noisy. The light hitting your eyes is noisy. The sound hitting your ears is noisy. Your own body signals are noisy. The environment changes constantly, so the brain behaves less like a recording device and more like a control system. It tries to keep you oriented and functional. This is why the interface idea in the original transcript is so tempting. It's trying to say, maybe the brain is not showing truth, but useful symbols. And there's a serious scientific version of that statement. Perception is optimized for action, not for exhaustive accuracy. Now, here's where we have to be careful, because this is where dramatic scripts sometimes slide from your perception is a model into everything is fake. That jump is not logically required. A map is not the territory, but the territory still exists. If you use a subway map, the lines are not drawn to scale. Stations are spaced evenly, curves are simplified, yet the map is still useful and still anchored in reality. If it weren't, you'd never get home. Your brain's model is like that. It compresses, it simplifies, it emphasizes what matters: edges, motion, faces, threats, food, social cues. And it hides what doesn't matter for survival. You do not perceive infrared light, radio waves, neutrinos, or the quantum fields that fill space. Not because they aren't real, but because your ancestors didn't need to see them to avoid being eaten. So, we've got the first big layer. The world you experience is not raw physics. It's a survival-optimized interface. Now we connect this to solidity, because this is where most people feel the argument in their bones. Solidity feels like the most real thing in the world. You bump into a table, and you learn very quickly that the table does not care about your philosophy. So why would anyone claim solidity is an illusion? Because the thing you call solid is not made of tightly packed little bricks touching each other like Legos. At the microscopic level, matter is mostly empty space, and the feeling of contact is produced by forces, especially electromagnetic forces, preventing atoms from occupying the same states. But before we go there, we need one more piece from the brain side. Your sense of solid contact is itself a perception. When you press your finger against a table, your nerves detect pressure and deformation. Your brain interprets that as touching a hard object. But what you're actually experiencing is your skin's interaction with fields and electron clouds. And the reason this matters is, your brain is extremely good at turning invisible causes into simple experiences. You don't feel electromagnetic repulsion. You feel hard surface. You don't feel photons scattering. You feel red apple. You don't feel air pressure waves. You feel music. So the brain builds the human-level world, a world of objects, surfaces, and events that sits on top of the physical world like a user-friendly layer. A life analogy. A car dashboard. When you drive, you don't watch fuel injection timings or engine temperatures at a microscopic level. You watch a speedometer, a fuel gauge, and a few warning lights. Those symbols represent deeper processes. They're not the processes themselves. The dashboard is not fake. It's simplified. Your experience of reality is the dashboard. Now, this is where the story opens into physics, because once you accept that perception is a constructed model, you're prepared for the next surprise. Physics itself suggests that objects are not fundamental in the way we naturally think. Not because physicists want to be mysterious, because the equations and experiments keep pointing that way. Modern physics describes matter in terms of fields and interactions. The vacuum isn't empty, and the solid world is built from rules that are real but not visible to your senses. So the natural next step is, if your brain gives you the dashboard view, what does physics say is going on under the hood? That's where we go next, into matter, fields, the empty space that isn't empty, and why stuff is less like tiny marbles and more like stable patterns in an ocean you can't see. Let's take the most ordinary thing you can think of, a table. Not a mystical table, not a what is the meaning of table table. Just a table you could knock on right now to prove to yourself that reality is, in fact, not a rumor. Knock knock. It feels solid. It sounds solid. It behaves solid. So when someone says matter isn't really solid, your first instinct is correct. That sounds suspicious. But here's the key. Nobody is saying the table isn't real. They're saying the story in your head, solid means packed stuff touching stuff, is not the story physics tells at the deeper level. Physics says the table is real, but solid is a behavior, not a basic ingredient. A good way to start is with the most useful mental flip in modern physics. Particles are not tiny, hard beads. In modern quantum physics, particles are better thought of as excitations of fields. If that sentence sounds abstract, let's make it feel normal. Imagine the ocean. The ocean is the medium. Waves are patterns traveling through it. A wave is not a separate thing made of separate wave stuff. It's the ocean doing a particular motion. Now, take that picture and swap the ocean for a field. A quantum field fills space. A particle is like a ripple, an excitation of that field. It's a stable, quantized pattern, not a tiny marble. That's why in particle physics, you can create and destroy particles in collisions. You're not breaking marbles. You're rearranging field energy into patterns that count as particles. So, electrons are excitations of an electron field. Photons are excitations of the electromagnetic field. Quarks are excitations of quark fields. This isn't just a metaphor. It's the framework modern particle physics uses because it matches experiments extremely well. Now, let's bring this back to the table. Why does the table feel solid? Because atoms don't like being shoved into the same space in the ways your intuition imagines. At the atomic scale, the stuff that matters most for solidity is the electron cloud around atoms and the quantum rules that govern electrons. When you press your finger into a table, the atoms in your finger get very close to the atoms in the table. What happens next is not little billiard balls touching. It's mostly electromagnetic repulsion and quantum constraints that prevent the electrons in your atoms from occupying the same states as the electrons in the table's atoms. In human language, the table resists you because the laws of electromagnetism and quantum mechanics enforce boundaries. A life analogy that lands quickly. Think of magnets. Two magnets can push each other away without touching in the way you imagine touch. You feel a force, a barrier, but there's no solid wall. It's an interaction. Your finger and the table are not magnets, but the key idea is similar. The resistance you feel is an interaction field preventing overlap. So solidity is not stuff packed tight. It's rules pushing back. Now, here's the fun twist. Most of the atom is empty space. If you take an atom and scale it up so the nucleus is the size of a pea, the electrons would be far away, like tiny specks at stadium distances. The atom is mostly volume where there isn't dense stuff in the everyday sense. And yet the table is solid because the interactions fill that space. The rules are active throughout. This is why empty and nothing become tricky words in modern physics. Because even if space has no atoms in it, it can still have fields. And even if a field has no obvious particles in it, it can still fluctuate. That's the next concept, vacuum. The vacuum sounds like nothing. But in quantum field theory, the vacuum is not a blank zero. It's the lowest energy state of a field. And quantum systems do not sit perfectly still in a sharp classical way. They have fluctuations. So, empty space is more like a quiet room with a faint hum than a room with the power cut. You don't see it with your eyes, but it has measurable consequences. A listening friendly analogy. Think of a calm lake. Even when the lake looks still from far away, it has ripples, microwaves, random motion at small scales. The stillness is a coarse-grained view. Zoom in and you see activity. Quantum vacuum is like that, but with field fluctuations instead of water waves. Now you may be thinking, okay, but if the vacuum is active, why don't we notice it all the time? Because the effects are usually tiny at human scales, or they cancel out, or they only show up under very controlled conditions. But they're not imaginary. The broader point for our story is this. At the fundamental level, physics doesn't start with objects, it starts with fields and interactions. Objects, tables, chairs, you, are stable patterns and organizations of those fields. This supports the interface vibe of the original transcript without needing to get dramatic. The world of everyday objects is a higher level layer. It's real. It's just not fundamental. This is a common pattern in science, by the way. You see it everywhere. Temperature is real, but it's not a fundamental particle. It's a bulk summary of many particles' motion. Pressure is real, but it's not a separate substance. It's a collective effect of collisions and forces. Traffic is real, but it's not a new material. It's many cars interacting. So solidity can be real while also being emergent. Now, let's connect this to one more idea from the transcript: the feeling that reality might be rendered. People hear about quantum fields and vacuum fluctuations and say, "So, is the universe like a simulation?" Careful. You don't need simulation language to say something meaningful here. The safer, more scientific claim is, the universe is structured by information-like constraints, and our everyday objects are compressed, stable summaries of deeper dynamics. That's enough to make reality feel less obvious, without jumping to someone is running us on a server. Now we're ready for the next layer, because once you accept that matter is field behavior and that even vacuum isn't a boring nothing, you're prepared for quantum mechanics' most stubborn lesson. Measurement is not always like classical, revealing what was already there. In many quantum experiments, what becomes definite depends on the measurement setup. Not because humans have magical eyeballs, but because the system plus measurement device is part of the physics. That's where we go next. The double-slit story done carefully. The witch path idea. Bell's theorem and what it really forces. And how to separate solid experimental facts from the more dramatic interpretations. If part 1 was, your brain builds a model, and this was, matter is fields and rules, the next step is, quantum mechanics explains why the deep layer doesn't behave like everyday objects, and why our interface-like experience might be the only stable way to navigate it. Now we step into the part of modern science that makes confident people suddenly start speaking in softer voices. Quantum mechanics. Not because it's mystical, not because it's anything goes, but because it's one of the rare cases where the universe behaves consistently, while refusing to behave intuitively. And here's the first thing to get straight, because a lot of dramatic scripts blur it. Quantum mechanics is not your mind creates reality. Quantum mechanics is the way nature assigns probabilities and correlations is different from classical expectations. The experiments are real. The math is reliable. The weirdness is not optional. But what the weirdness means, what story you tell about it, has multiple interpretations. We'll keep it grounded. We'll separate what's measured from what's philosophical. And we'll use analogies that don't require you to stare at equations until your soul exits your body. Let's begin with the most famous story in the quantum genre, the double-slit experiment. Imagine you have a wall with 2 thin openings, 2 slits, and behind it a screen that records where particles land. Now you fire particles toward the slits. For simplicity, think of electrons, but photons also work. The key point is, you're sending them one at a time, like the world's slowest machine gun. If electrons were tiny classical pellets, you'd expect a simple result. Each electron goes through one slit or the other, and you get 2 blobs on the screen. one blob for each slit. But what you actually get, if you don't try to find out which slit each electron went through, is an interference pattern. Many stripes. A pattern we normally associate with waves. And the truly unsettling part is, you can send electrons one at a time, and over time the interference pattern still builds up. It's as if each electron behaves like a wave that goes through both slits and interferes with itself, but then lands as a single dot. So far, weird, but manageable. Okay, electrons have wave properties. Now comes the turning point. If you add a detector to check which slit the electron goes through, if you try to get which path information, the interference pattern disappears. You get the two blobs, as if the electron behaved like a particle again. So, the outcome depends on what information the experiment setup makes available. This is where people often say, observation changes reality. But we should translate that into more precise, less spooky language. When you arrange an experiment so the paths are distinguishable, interference goes away. When you arrange it so the paths are indistinguishable, interference appears. It's not human eyeballs doing magic. It's the physical availability of which path information, which usually involves interaction with a measuring device and the environment. A life analogy. Imagine a room with two doors and a slippery floor covered in powder. If you want to know which door someone used, you set up a camera or you add a loud, squeaky mat. Either way, you've changed the situation. The person interacts with the detection setup. Their path becomes tagged. Quantum systems are like that, except the tagging doesn't just add noise. It changes what kinds of patterns are possible because of how probability amplitudes combine. Now, if you stop right here, you might conclude, reality isn't settled until measurement. That's close to one major interpretation, but it's not the only one. It's better to say, quantum theory predicts probabilities for different outcomes. Those probabilities depend on the measurement context. When a measurement happens, you get a definite outcome. And the big open question is, what counts as a measurement, and why does it produce one specific result? That question is called the measurement problem. It's not about whether quantum mechanics works. It works. It's about what the theory is saying about reality underneath. If you want a simple way to feel the measurement problem, think of a coin. In classical life, a coin is either heads or tails, even if you're not looking. Looking just reveals it. Quantum systems are different. Before measurement, the theory describes them in a way that's more like a weighted combination of possibilities. It's not that the system is secretly one outcome, and we just don't know. In many cases, the formalism treats the possibilities as simultaneously present in a meaningful mathematical sense. Then, measurement gives you one outcome. So people ask, where did the other possibilities go? That's where interpretations enter. Different interpretations answer that question in different ways. Some say the wave function collapses into one outcome when measurement occurs. Some say all outcomes happen, but in different branches, many worlds. Some say the wave function is not a physical thing. It's information about our knowledge, and collapse is an update. Some try to modify the theory, so collapse is a real physical process that happens spontaneously sometimes. You don't need to choose one to understand the experiments, but it matters for how dramatic you make the story. Now, The double slit is the appetizer. The main course, in terms of what experiments force us to accept, is Bell's theorem. Bell's theorem is one of those results that sounds technical, but the core message is surprisingly simple. It says, if you assume the world works like this, 1. Properties are predetermined. Realism in a classical sense. Particles carry their answers with them. And 2. No influence travels faster than light, locality. Then certain statistical correlations have a maximum limit. Bell derived inequalities, bounds on how strong the correlations can be under those assumptions. Then experiments were done. And nature violated those bounds, which means you can't keep both assumptions at once. Something has to give. Now, here is the place where the original transcript's tone tends to sprint into the spooky forest. We'll stay on the well-lit path. Bell violations do not mean you can send usable messages faster than light. They do not mean you can build an instant communication machine. They do not mean your thoughts zap reality across galaxies. What they mean is more specific and more interesting. Quantum mechanics predicts correlations between distant measurements that cannot be explained by local hidden variables, by the idea that each particle carries a pre-written instruction sheet, and nothing else happens. So, you have a menu of uncomfortable options. Give up local realism, the combined classical idea of local causes, plus pre-existing values. Accept some form of non-locality in how the theory relates outcomes. Or accept that measurement outcomes are not simply revealing pre-existing properties. Different interpretations choose different meals. None of them are a free lunch. A life analogy. Imagine two friends who agree on a secret strategy before entering separate quiz rooms. You might think they could produce correlated answers by pre-planning. Bell's result is like proving that no pre-planning strategy can match the correlations you actually observe, unless something else is going on that violates the assumptions. So, quantum correlations are stronger than any local pre-written plan can produce. Now, there's another family of experiments that often gets described with dramatic language: delayed choice and quantum eraser experiments. These are real experiments, and they're fascinating. But the common dramatic phrasing, "the future changes the past," is usually more theatrical than necessary. Here's a cleaner, calmer way to understand the vibe. In certain setups, you can choose to preserve or erase which path information after the particle has passed the slits, or in entangled setups, after the partner measurement is made. When the data is sorted in particular ways, interference patterns appear in the subsets where which path information is unavailable, and disappear where which path information is available. This can feel like your later choice determines what the particle did earlier. But the more careful framing is, the patterns you see depend on how you correlate and condition the data, and on whether the experimental setup makes path information available. The story you can tell about the particle's path is not always a single classical narrative. In other words, quantum mechanics is warning you that classical path-based storytelling is sometimes the wrong tool. It's like insisting that a song must be described only as a sequence of drum hits. Sure, drum hits exist, but the song is not fully captured that way. Sometimes you need the whole waveform view. Sometimes the question which drum hit caused the chorus is just not the right question. Now, how does all of this connect back to our bigger theme, reality as an interface. Here's the connection stated plainly. Your everyday experience strongly suggests objects have definite properties at all times. Events have single histories. Measurement reveals what was already true. Quantum experiments suggest some properties don't have definite values until measured in a specific context. Some outcomes are fundamentally probabilistic, not just unknown. Correlations can exist that don't fit local hidden variable stories. The classical idea of a single history with hidden details is not always compatible with the data. So, the interface story is one way to say the world we evolved to experience is a stable, classical summary layer. It's what you get when countless quantum events are averaged, decohered, and turned into robust patterns. It's the layer where chairs stay chairs and tables stay tables. That word decoherence matters, and we should explain it simply because it's one of the most important bridges in the whole discussion. Decoherence is what happens when a quantum system becomes entangled with its environment in a way that effectively destroys interference between different possibilities. The environment soaks up phase information. The system stops behaving like a neat, isolated quantum wave and starts behaving like a classical object with stable outcomes. You can think of it like this. If you whisper a secret in an empty room, the information stays neat. If you whisper it in a crowded stadium, it gets scrambled instantly. In the stadium, the secret doesn't disappear, but it gets spread out into correlations with the environment in a way you can't practically recover. The neat interference story stops being useful. That's why everyday objects look classical. They're constantly interacting with trillions of environmental degrees of freedom. The quantum weirdness doesn't vanish, but it becomes inaccessible in practice. The interface becomes stable. This is a big reason physicists don't walk around worrying that their coffee mug is in two states at once. The mug is too entangled with the environment. Decoherence makes the classical story overwhelmingly good at our scale. So where are we now? We've built 3 layers. Your brain constructs a model for survival. Matter is fields and interactions. Solidity is behavior. Quantum mechanics forces a deeper kind of description where measurement, context, and correlations matter in ways classical intuition doesn't expect. Now we're ready for the next step. Because the transcript's boldest move is to say, maybe even space-time, the stage itself is part of the interface. That's where physics becomes cosmology adjacent and quantum gravity adjacent. Planck scales, emergence, entanglement as structure, holography as a clue. We'll keep it grounded, and we'll keep it honest about what's established and what's speculative. But the direction is clear. If the things on the stage are emergent patterns, it's not crazy to ask whether the stage is emergent too. If you've made it this far, your brain has probably tried to grab a lifeline by saying something like, okay, fine. Maybe matter is not little marbles. Maybe quantum behavior is weird, but at least space and time are the stage. The stage has to be real, right? That's a very reasonable instinct. And it's exactly the instinct modern physics has been poking at for the last century. Because when you try to combine the 2 big pillars of modern physics, quantum mechanics, rules for the small, and general relativity, rules for gravity, space, and time, the stage starts looking less like a solid platform and more like something that might itself be built from deeper ingredients. Not fake, not illusion, more like emergent. And emergent is a friendly scientific word. It means real, reliable, and measurable at your scale, but not the most fundamental layer. A classic everyday example is traffic. Traffic is real. It can ruin your day, it can be measured, it can be predicted. But traffic is not a fundamental substance. It's a pattern that emerges from many cars obeying simple rules. Or think about a wave in a stadium. The wave is real. You can film it. You can time it. You can cheer with it. But it isn't a separate entity floating above people. It's a coordinated pattern emerging from individual motions. So the question becomes, could space and time be like that? Not fundamental stuff, but stable patterns arising from deeper rules. This is where things get exciting, and where we have to keep our feet on the ground, because the ideas range from well-supported clues to bold speculation. Let's start with one of the clearest and most famous clues: black holes. Black holes are where gravity gets extreme. They're the universe's stress test for any theory of space-time. And they force a weird fact into the conversation. A black hole's entropy, its information capacity in a loose sense, scales with the area of its boundary, not the volume inside. That's deeply counterintuitive. In everyday life, if you want to store more stuff, you get a bigger box. Volume matters. A closet holds more than an envelope. But black holes don't follow that intuition. The bookkeeping seems to care about surface area. This idea is one of the reasons physicists began taking holographic thinking seriously. A hologram is a 2D surface that encodes a 3D image. You can tilt it and see depth, even though the information is stored on a flat film. So the holographic principle, in plain language, is a suggestion that the information describing a region of space might be encoded on its boundary, like a cosmic hologram. Now, we should be careful here. Holographic principle is not a proven statement about our entire universe in all details. But it's supported by strong theoretical arguments and by specific cases where we can show it works as a precise mathematical equivalence. One famous example is a relationship called ADN-CFT, which is a particular kind of holographic duality. If that sounds too inside baseball, here's a useful takeaway. There are serious reasons to think the universe might not store information the way your intuition says it should. And whenever information storage starts acting strange, it often points to a deeper structure underneath the thing you thought was fundamental. Here's a listening, friendly analogy. Imagine you buy a high-end suitcase. You assume storage depends on volume. Then you discover, weirdly, that the suitcase's maximum packing depends only on its surface area. No matter how deep it is, the packing limit tracks the outside. That would make you suspicious that you're not dealing with ordinary packing. You're dealing with some hidden rule, like everything inside is being compressed in a special way. Black holes are that kind of suspicious suitcase. Now, add another clue: entanglement. Entanglement is the quantum link between systems, correlations that are stronger than classical expectations allow, as we discussed earlier. What's new here is a growing theme in modern theoretical physics. Entanglement doesn't just connect particles, it might help build spacetime structure. This is a big idea, so let's make it feel simple before it feels grand. Think of a social network. If two people talk constantly, share friends, share projects, and coordinate everything, you'd say they're close in a social sense, even if they live in different cities. If two people barely interact, they're far socially, even if they live on the same street. Now replace people with quantum subsystems, and replace talking with entanglement. Some physicists suspect that what we call spatial closeness might, at a deeper level, be related to patterns of entanglement. Not literally, Facebook causes geometry, but the idea that connectivity in an underlying quantum description can correspond to the shape of space in the emergent description. There's even a famous slogan-like idea you may hear. Space-time is stitched together by entanglement. Again, not a settled fact about everything. But it's not random poetry either. It's motivated by how certain quantum gravity models behave. And then there's an even wilder cousin idea that sometimes gets mentioned alongside this. EPR, which loosely links two concepts, wormholes, Einstein-Rosen bridges, and entanglement, EPR correlations, as potentially related descriptions in certain contexts. You don't have to believe literal traversable wormholes are popping out of your lab experiments. The point is more conceptual. Deep quantum connections and geometric connections may be two ways of describing the same underlying structure in special cases. So, here's where we are so far. Black holes hint that spacetime stores information in an unexpected way. Holographic ideas hint that volume may not be the fundamental storage unit. Entanglement hints that distance might emerge from deeper connectivity patterns. That already supports the transcript's vibe. The stage might not be fundamental. Now, let's talk about the Planck scale, because it's the place where physicists suspect the smooth picture of space-time breaks down. At human scales, space looks smooth, like a continuous sheet. You can slide your finger along a table without noticing pixels.